I reproduced our solution, asymptotics of our solution at large positive x, and here is our saddle. So now let's investigate what's going to happen with our solution at large and negative x. So apparently our saddle is going to shift into the right-hand side of our complex plane. Right, so it's going to be here. As you remember, the second derivative of our exponential function, the exponent function, is 1, so it's independent of x. So the steepest descent direction for large negative x is going to be again the vertical direction. All right. Okay, let's write down. So x is as you remember as well, we need to, in order to understand how the contour should be deformed, when we try to just bend it through, so it passes through this saddle, we need also to write down, to shade the so-called allowed regions in the complex plane along which the contour can approach and leave the saddle. So they are like inclined by 45 degrees from this steepest descent direction. All right. And here is a puzzle. So somehow we should, in order for this contour to pass through this saddle, we somehow need to bend it. So actually we could shift it in this direction, right? So it could technically pass here like that. But, so it passes like this. But then in order to get back into this left-hand side of our complex plane, it should bend quite significantly. So it should go like this, probably, and then it should return back. So this is the proximal deformation of our contour if you want it to pass along through this saddle. And this is a problem because here it passes through this forbidden region. So this is the area which lies above this saddle. So that kind of deformation is not possible, so we should forget about it. Okay, so then how do we find the asymptotic of this solution defined by this equation, by this contour, when x is large and negative? Well, there are additional special points in complex plane which are branch points, here and here. And when we move the contour in the complex plane, you see it kind of, it touches, when we try to shift it, it always touches this -1 branch point. So obviously, we suspect that the asymptotic of this solution is defined by the vicinity of this branch point. By the way, sorry, it's C2, of course. C2. Right. So if the solution, so whenever we try to deform the contour, it will touch this branch point. So what's the behavior of our exponent function in the vicinity of this branch point? So here is our exponent function. And so if t is equal to -1, so let's make a small deviation from this -1, like -1 plus s. So, and then f of -1 plus s is obviously x minus x plus sx and plus 1/2 minus -2 minus s, sorry, and plus plus s squared over 2. Right. So as you see, if s is small, so if the deviation from this branch point is small, then we can discard s squared over 2 term. So we can leave actually only this as x and s terms. That's it. So the structure of our integral is greatly simplified in the vicinity of this point. So what we can do actually, we could shift the contour in this right direction. And if since x is negative, the steepest descent direction from this branch point is going to be which one? It's going to be, actually it's this direction. It's horizontal right direction, right? Because it's defined by this as x, well, as x minus x, s actually, but since x is large, then basically we can discard this term, and this term. Right, so this is basically the dominating behavior of our exponent. And since x is negative, then s should be positive, and this will correspond to the steepest descent direction when we go along, when we move from this branch point. So the idea is to shift the contour to the right, like that. But of course, it can't, so it should bend when it passes through this branch point. So the deformation is like this, right? And then, but when it goes from this point, again, the steepest descent direction is this direction, right? But it can't pass in this direction because the branch guard prevents it from doing this. So what would be the way out from this situation? Well, the idea that we deal with multi-value function here. I mean, this square root of t squared minus 1. So we can represent it as a single-valued function on a Riemann surface. And its Riemann surface consists of two Riemann sheets. And here, let me actually show you how the correct deformation looks like. So to understand what is happening, we should draw the Riemann surface. So here it is. And the contour now slips into the lower Riemann sheet of our, like that, Riemann sheet of our complex plane. And it continues in this upward direction along this steepest, in the upward direction, while traveling along this lower Riemann sheet. So okay, let's return to our whiteboard. And so here we go. So we write it down with a shaded, with a dotted line. So here the contour slips below the upper Riemann sheet onto the second Riemann sheet, and then continues in the steepest descent direction on the lowest Riemann sheet, like that. And then it bends again in the correct direction and goes like this. Right. So this is how we compute the asymptotics in this situation. So here we go. Now we expand, what we do, we expand our exponent and our g function in the vicinity of -1 point. So let's do this. So our exponent is e to minus x plus x, actually x minus 1. Let's skip this minus 1 times s. So this is their exponential function. But now dt is obviously equal to ds over the square root, okay, of t squared minus 1. So if we compute it, the modulus of t squared minus 1 is going to be equal to 2s. So this is square root of 2s. But we need to find the correct sign for this t squared minus 1. So here is the region where our g function is positive. And now we approach this function, this branch point from the right-hand side. So this complex number, t minus 1, made the full pi rotation in the counterclockwise direction. So the delta argument of t minus 1 is minus pi. Right. This complex number, t plus 1, doesn't make any rotation. So the total change of the argument of our square root function is minus pi. And since we have a square root, it's going to give us minus pi by 2. So what we have here is e to I pi by 2 in their denominator. So this is our integral, and it's taken over ds from, so we approach it from big S to small s, so it's taken from plus infinity to 0. Right, and then we circle around this point, and well, you're kind of already guessing where I'm heading to. So we want to actually express these two integrals, reduce these two integrals to gamma function. Right, so now we go in this right direction from small s to big S, so the integral is going to be from 0 to plus infinity. We slip into another Riemann sheet below this one. So now the change of the argument of this t plus 1 function is going to be, so here it's some value, and then it rotates in the counterclockwise direction by 2 pi. So we have a similar integral. ds over square root of 2s. But the change is that, so here is pi rotation and yet another 2 pi. So the full change of the argument of this square root function is 3 pi. And since it's square root, it's 3 pi by 2. So it's e to 3i pi, sorry, minus 3 pi by 2. And since it's in denominator, it becomes plus 3 pi I by 2 in the denominator. Right, so, and here we go. So this is a combination of two integrals. And what we get in the end, e to minus x times, right, times, so let's actually, so it's, let's add them. So it's I pi by 2, negative sign, and here's another negative sign. So it's minus 2 plus I pi by 2, and e to x minus 1 s ds over the square root of 2s. And this is nothing but a gamma function, right? So now we may make another change of variables. Say v is equal to, okay, so x is negative, keep in mind. So v is equal to whatever, minus, actually plus modulus x plus 1 times s. So, and well, since x is large, we can discard these ones. So, and the answer is minus 2 e to minus x times I plus I pi by 2, so it's I. And here we go. This is a gamma function of over 1/2 divided by, so let's see, it's divided by the square root of x, right? Modulus x, sorry. When x tends to minus infinity. So have I forgotten something? Yeah, square root of 2. Right, so this is our asymptotics at large negative x. And you see that we clearly have a problem. So we did find the asymptotic correctly, but since x is large and negative, this exponential factor leads to the exponential growth of our solution. But the requirement is that we should get the bounded solution at both x positive, large positive, and x large and negative. So this contour clearly doesn't give us the correct solution at both x tending to plus and minus infinity. And the same situation, the same problem is takes place when we consider the right-hand side contour. So it's kind of symmetric because it will give us the correct behavior, the good behavior for large negative x, because we will have here this saddle, and the solution is going to be like e2 minus x squared over 2. But when x becomes positive, then again we'll have to deal with this unsuitable deformation. And the contour, the solution, will be defined by the vicinity of this branch point. So this branch point is 1, and the solution is going to be dominated by the exponential factor e to 1 times x. So it will behave like e to x at large and positive x. So again, the solution defined by the third contour is going to give us exponential growth at large positive x. So our last hope to find a bounded solution is the middle one, the solution which we denoted by the contour which we denoted by C1. So let's actually investigate this behavior, the solution defined by this contour.